So let's talk about complex zeros, and we're going to talk about this in terms of the fundamental theorem. And all a complex zero is, or a zero first is, remember a zero is the solution to any polynomial function. And in general, we're going to use our zeros to look at the graphs of polynomials. And so when we have a real zero, when we talk about a real zero, we're talking about where is it crossing the x-axis. So real zeros are where we cross our x-axis. So basically, they're x-intercepts. And this right here would be a real zero for us. That is a real zero. Now, this polynomial also has other solutions, though. In this case, you can tell it's going to be an odd because of the end behavior. So it's going to be at least 3 solutions here. And that's because the end behavior starts down and it finishes up. So it finishes in opposite directions, which means we're going to get an odd function. All right. So the other solutions then are going to be what we call imaginary. And they're imaginary because we don't know where they're crossing the x-axis at. But they are going to actually give us a solution for the polynomial. Those new solutions are going to be what we call complex zeros. And they involve the imaginary unit I. So an imaginary unit is just an imaginary number is anything with the letter I, or we use for I to represent the imaginary unit. And when we talk about a complex zero is a solution that can be written in the form of a plus bi, where a is the real part and bi is the imaginary part. And so when we go to solve these particular polynomials now, the graph will look something like this here, where you won't be able to see from the graph where the actual solutions are, because we no longer have just a real part. We now have this imaginary part that's going to produce solutions as well. And the nice thing about imaginary numbers is that they always come in pairs. An imaginary number will always come in some kind of pair. They always come in pairs. And because they always come in pairs, we get what's called the conjugate pair for an imaginary number. And a conjugate pair just says that if we have the number a plus bi, then its conjugate is the number a minus bi. And all it means is we're just going to change the sign in the middle or give the opposite sign of whatever you're getting. So if I have a plus in the middle, the conjugate pair is a minus. If I have a minus in the middle, the conjugate pair is a plus. And it always affects the I part of it, or the imaginary part of the equation. So we're going to do some things with this. This right here, the conjugate pair and the zeros, are going to allow us to develop what we call our fundamental theorem. So the fundamental theorem of algebra states that for every polynomial, if you put it in standard form and you find its leading coefficient and you look at its degree, whatever that degree is, or whatever the highest exponent in the polynomial is, it'll always give you the number of zeros, the maximum possible number of zeros that that polynomial will have. And those zeros can be either real zeros, which is what we've looked at before, or now they can be, if they're not all real, then the remaining zeros are going to be complex zeros. And because we deal with complex numbers, and complex numbers happen to come in conjugate pairs, from the fundamental theorem of algebra, we get the complex conjugate root theorem. And all it says is that if a plus bi is a solution, so one of your solutions, so if your solutions are, if you have a plus bi, then another solution must be a minus bi, its conjugate. And because of this, anytime you have a complex zero, you're always going to look for its conjugate pair to give you all the zeros. So we're going to talk about that with the fundamental theorem to help us actually find the number of zeros and the actual zeros when we look at an actual equation. So let's look at a couple of examples. So let's look at these two examples on finding the remaining zeros if we are already given zeros. And the first one says a polynomial of degree 5, whose coefficients are real numbers, has the zeros 1, 5i, and 1 plus I. Find the remaining two zeros. And the big thing here is that we know that the degree, so when this is written in standard form, or the polynomial of some form, ax to the n plus bx to the n minus 1, and it's decreasing all the way down to some constant, we know that our degree is this first term in the leading coefficient. We know it's that, and that's the degree. And here, we know that our degree is equal to 6. And the fundamental theorem of algebra tells me that that means that I have 6 total zeros for this particular equation. And right now, they've given me 3 of those solutions, 3 of those zeros, where one of them is a real solution, and the other 2 are going to be imaginary. And I know they're imaginary because I have eyes here. So what that tells me that each one of those solutions will come and give me a particular other solution because it comes in a pair. And again, I'm sorry, I said this was degree 6. This is actually degree 5. This is actually degree 5. So our degree is 5. So that means, look here, I have 3 solutions already. Because these come in pairs, that's an additional solution, and that's an additional solution. That's going to be all 5 zeros. It's going to be all 5 zeros that I need there. So to find the other 2 zeros, all I do is I take my imaginary solutions, the first one 5i, and because it's 5i, that's a positive 5i, that also means that negative 5i is its conjugate pair. So that's an additional solution. And then the other one is 1 plus I. And because it's 1 plus I, remember, to get the conjugate pair, you just flip the sign on I. So this will be 1 minus I. So here are 4 solutions, and the 5th solution we said was 1, which was given to us already. So here are what all my x's are going to equal when I solve them. Now, the next one, find the remaining 2 zeros of a polynomial of degree 6. Whose coefficients are real numbers that has the zeros 2, negative 3, 2i, and 1 minus 2i. This time I know my degree is 6, so that means I should have 6 possible solutions for this particular equation, or this particular polynomial. I know that 2 of those solutions right now are going to be real numbers. These are real. And then that leaves me with the remaining 2 to be imaginary. Well, if you have an imaginary solution, remember, you have to have a pair for it. So here, I know that if I have 2i's solution, its conjugate, negative 2i, is also a solution. And I know if I have 1 minus 2i is a solution, its conjugate, 1 plus 2i, is a solution. And so this is how we use the fundamental theorem of algebra, and the fact of the complex conjugate theorem, we use it to actually find all the solutions of a polynomial. So now that we know how to find the solutions of a polynomial and find all those zeros, we should also be able to go in reverse order and find an actual polynomial given zeros. And so here, we've done this before. We have to write the equation of a polynomial given its zeros. And remember, to do that, you need to write the factors. Well, when you have a real solution, it's very easy to do that because all it means is you change the sign of the zero. So in this particular equation, we want to find a polynomial f of degree 4 whose coefficients are real numbers and that has zeros 1, 1, and negative 4 plus I. Well, remember, because it's of degree 4, that means we should have at least 4 solutions. And in this problem, they've given us zeros 1, 1, so that means I had a multiplicity of 1, a multiplicity of 2 for 1. And then we had negative 4 plus I. So that's only 3 solutions I'm looking at. Well, remember from what we just talked about, the complex number actually has a pair. And it's negative 4i, negative 4 plus I. Its pair would be negative 4 minus I. Negative 4 minus I. So there goes our 4th solution. And for the real part, remember when we write the real, if the 0 is 1, then our real part is just going to be x minus 1 as the factor. We need to write the factor for that. And all you do is you change the sign on the 0. So if this was a 1, it became a negative 1. And notice we have that written here twice. So we can write it as x minus 1 times x minus 1 again. Or you could actually write it as x minus 1 squared. Since we're going to be trying to find, since we're going to try to find the polynomial, we're actually going to leave it as x minus 1 times x minus 1. And we can see all the factors. Now, the complex part, you're doing the exact same thing. Because when we write a solution as a factor, if k is a factor, if k is a solution, then the factor then x minus k is a factor. And we use that over here to show that x minus 1 and x minus 1 are the factors from the solution, or the 0 of 1. The same thing works with the complex part. And you write the complex part like this. If negative 4 plus I is the solution, then x minus negative 4 plus I. Negative 4 plus I is also a solution. And likewise, x minus negative 4 minus I is also a solution. Now, we need to clean this up. And we can clean it up by distributing the negative across this part here and across that part there. So when we distribute that negative out, here's what we're going to get. Distributing the negative on the first part, the factor becomes x, negative negative is positive, x plus 4, negative positive is a negative, minus I. That's one of your new solutions. That's one of your new factors. The other factor, distribute the negative here again and here. Negative negative is positive, that's x plus 4. And back here you get a plus I. So the new polynomial you're going to work with then, or the new factors are going to be x minus 1 times x minus 1 times x plus 4i, x plus 4 minus I times x plus 4 plus I. And notice how this has changed. The negative 4 changed to a positive 4. And then your plus I here became a minus I. And your minus I becomes a plus I. To shorten this, you're always going to change whatever the number part of the solution is, the real part of the solution. Change the sign on the real part. And then write the plus I and the minus I as pairs together like this. And so from here, we're going to distribute. And we're going to distribute like this. We're going to distribute the real to the reals first. And we're going to distribute the imaginary to the imaginary together as well. So when I do that, x minus 1 times x minus 1 is x squared minus 2x plus 1. And I got that because I did x times x is x squared. X times negative 1, negative x. Negative 1 times x, negative x. So that's negative 2x. Negative 1 times negative 1 is a positive 1. And then I'm going to do this right here. And when I do the imaginary part back here, I get x times x, x squared. X times 4, 4x. X times positive I, positive xi. 4 times x, 4x. 4 times 4, 16. 4 times I is a positive 4i. Negative I times x, negative ix. Negative I times 4, negative 4i. Negative I times a positive I. And remember, I times I is I squared. So what you have here is a negative I squared. And so when we clean things up, the nice thing about the conjugate is that a lot of things are going to disappear. For instance, xi and positive xi and negative ix are the same terms. They cancel. 4i and negative 4i cancel. And then when we look at this, you have this negative I squared. Remember, I squared is equal to negative 1. That means that negative I squared is equal to, well, negative 1 times the negative is a positive 1. So this term right here is just positive 1. And the nice thing about this is notice that when we wrote it out, every term had an I. But now all of the I's disappeared. And so you're left with only terms that have an X. And that's what the conjugate did for us. That's why we use the conjugate pair. We want to get rid of the I's. And so now when I look at this, I can go ahead and clean this up further. So remember in the front, I just have x squared minus 2x plus 1. And then in the back, I now have x squared. I have 4x and 4x. That's 8x. And then I have 16, and it's plus 1, so that's plus 17. And again, the final step now is to go back and distribute. So to distribute these terms out, x squared times x squared is x to the 4th. X squared times 8x, positive 8x cubed. X squared times 17 is 17x squared. Next thing is the 2x. Negative 2x times x squared, negative 2x squared. Negative 2x times 8x, negative 16 x squared. This should actually be negative 2x cubed. I'm sorry. And then negative 2x times a positive 17 is a negative 34x. And then in the final part, we're going to do this 1. So we get 1 times x squared, x squared. 1 times 8x, 8x. 1 times 17, positive 17. And now we can combine like terms. So here, I see that my lead term, x to the 4th, is the only x to the 4th term. I have 8x cubed and negative 2x cubed. So that's going to be a positive 6x cubed. I have 17x squared, negative 16x squared, and positive x squared. So that's going to be 17 minus 16 is 1, plus 1 more is 2. So that's 2x squared. I have 34x, negative 34x, and positive 8x. That'll be equal to a negative 26x. And then I have just the 17 in the back. So here is the final polynomial that we want to calculate with those zeros that we're giving and of degree 4. Notice that the highest degree here is the degree 4.